do we now prove that this is in fact possible? So to check that in fact this is the best possible, let's actually consider a related question, which is, can you give me bounds on what is not achievable? In other words, suppose somebody says, this roughly is 5,142 and change. Okay? So that's the amount. Now, can you convince me that there isn't any solution that gives me a profit of, let's say, 100,000? I mean, that's yes.
You solve the system with two equations with x1 and x2.
Mm-hmm.
Get an upper bound of 4x1 of 4,500 over 7.
Could you say that again?
If you subtract from the first equation,
mm-hmm.
subtract the second one, multiplied by 4,
mm-hmm.
you get the x1 is less than or equal to 4,500 over 7.
Okay.
So then, then you can also, from that solution, get an upper bound for x2. And since the function we're maximizing has a plus side between the two, you would want to take the maximum value of both.
Okay, so let's actually, why don't you repeat it slowly? So you take this equation, subtract this from this.
Subtract 4 times the second one from
4 times from the second one from
that one.
This one. Okay, so let's actually do this. So let me just call this 1 and 2. And I'm going to do 2 times 4. That gives me 24x1 plus 20x2 is at most 24,000. Okay, and I want to subtract this equation from that one. Okay, so let me do minus. So 1 times negative 1, that gives me minus 10x1 minus 20x2 is
you get 14x1. Oh, over there it's 15,000.
But it's going to be at least.
Right. No.
So there is a problem, right? So the suggestion was that you multiply this by some number, then subtract this, but when you subtract inequalities,
So you can just draw a graph and make like 2 lines in the bounded area, and you see the x1 and x2, but they just cannot fall out of the area.
Okay, so here's another suggestion, which is this is a problem involving just 2 variables. So you can draw a graph, okay? And your graph is going to identify a certain region of x1 and x2 that are all valid solutions. Okay? And then maybe use some property of this region to claim that this is the best possible. Okay? So that is a good suggestion. The only difficulty is that, of course, that works for this problem and all 2 variable problems. Maybe if you can visualize 3D graphs, then it works for all 3-dimensional problems. But if you have 10,000 variables, then that's a little hard to do. Okay. But that will work. Okay. But of course, it still requires intelligence on the part of the verifier, right? That you have this region, and within that region, of course, that region contains infinitely many feasible points, and you want to make a statement about all possible points in that region. So something that's algebraic, you're converting it into something geometric and more visual. So one might be able to use some properties and then sort of intuitively convince oneself that this is the best possible, but that still isn't a clean proof that this is the best possible. Okay. But let's actually set this question aside for a moment. Okay, so let's not worry about the optimality of this particular solution. Let's actually try to get bounds on values of z that are above which there is no solution. So in other words, can you convince me that there is no solution with value, 100,000? Yes.
Well, x1 can be at most 800.
Uh-huh.
And, the coefficient in front of x1 is bigger than the one in front of x2.
Right.
So if you plug 800 into your z, then you get 4,000 or whatever. So.
Actually, so I could, okay, so this is a good point. So certainly x1 is at most 800. Okay. So the maximum profit I can achieve from x1 is 4,000. Okay. But I might be able to achieve some money from x2, right? Of course, x2 is constrained as well. This says x2 is at most 120. Is that right? 1,200. Okay. So here's one idea that might work, which is, so we know x1 is at most 800. Okay. And we also know from 2, x2 is at most 1,200. Okay? Now, the reason why you know this is because x1 is required to be non-negative, and therefore the smallest this can be is 0, and so the largest that x2 can be is 1,200. Okay? Okay? And therefore, 5x1 plus 4.5x2 is definitely less than 5 times 800 plus 4.5 times 1,200, whatever that quantity is. Okay. So this, I think, works out to 4,000 plus 4,800 plus 600. Yes?
I have a question here, because if there's no constraint on x1, let's say x1 can equal to whatever value, and if you use some kind of method to solve these kind of inequalities in simplex method, you would still get the same answer, I guess.
Yes.
But in that case, we don't know x1 must be less than 800. How can we just right here?
I agree. So the criticism is, of course, you may not have a constraint like this, and it may not be that you're able to look at one equation and derive bounds on x2 or x1. For instance, if this were minus 6,1, okay, then this idea is not going to work. Okay? But right now we are only exploring what one might be able to do. I don't claim that this is the right way to look at it or etc. This is just one way to get bounds. So in other words, if somebody comes to you and says, oh, I have a way of making $10,000 profit per week using, for this particular flexible manufacturing problem, then you know not to believe that person, because now you have a proof that no matter what you do, you cannot do better than 9,400. Okay? Notice that this doesn't say that one can actually achieve 9,400. This only says that if you obey the constraints of this problem, you definitely cannot get better than 9,400. So what you can do, the best possible profit that you can extract out of all of this is at most 9,400. Okay? There is still a big gap between this and this, but at least it is a bound. Okay? Yes?
You can use the equation 2, as we know that x1 and x2 are non-negative. We know that 5x1 plus 4.5x2 is less than 6x1 plus 5x2. So it's less than 6,000.
Okay. Okay, very good. So if you can do this, okay, notice that this only says it looks at x1 in isolation, looks at x2 in isolation. Okay? Even within these restrictions, you observe that if x1 is 800, as you assume, then x2 has to be at most, 4,800 of this resource is going to be consumed by 6x1. Okay? So if x1 is actually 800, x2 has to be at most some much smaller quantity, not 1,200. Okay? So we are being too conservative in doing our estimates of the best possible x1 and x2. We are looking at these two in isolation, whereas in reality, any positive production of x1 consumes resources, which is going to limit the amount of x2 that you will be able to produce. Okay? And one way of seeing that is exactly what you said, which is we don't have to do these kinds of calculations. Just equation 2 gives us a bound on what is best possible. Okay? So we know that if you respect this constraint, 6x1 plus 5x2 is at most 6,000. And we know that our objective function is term-wise dominated by this inequality. Okay? So in other words, in other words, 5x1 plus 4.5x2 is at most 6x1 plus 5x2, which is at most 6,000. Okay? So this comes from constraint 2, and this inequality is true because x1 and x2 are non-negative. Okay? So you now have a better bound on the best possible value. Okay? So initially we said the objective value, the maximum profit, is definitely at most 9,400. Now we know that it's at most 6,000. Okay. Any questions about this reasoning? Now, what would be very nice? What would be nice is a way of getting exactly that quantity here. Okay. What would be nice is something like 5x1 plus 4.5x2 is so let me just write the exact quantity. Okay. So if one can derive this, if one can derive something like this, then that would prove that this solution is the best possible. Okay? I mean, this seems like an obvious, silly point, but this is actually quite important. So I want to make sure that everyone understands it. Here, we used a trivial argument to observe that the maximum profit in our problem cannot be better than 6,000. Okay? Now, using some intelligence, we figured out that this is a solution. We suspect that it is optimal. And one way of proving that would be, if possible, to somehow be cleverer in operating the constraints of our problem and derive an inequality that looks like this, okay? Where the right-hand side is exactly that term. Now, if we do that, then we know that the solution we found is the best possible value, because we've derived an inequality from the constraints of the problem that says that your profit cannot be better than this quantity. Okay? Yes?
Go over again how you know 5x1 plus 4.5x2 is less than 3.66.
Okay, so that's because x1 is non-negative, so 5x1 has to be at most 6x1. Right? Similarly, x2 is non-negative, so 4.5x2 is at most 5x2. If x1 were allowed to be negative, of course, this inequality is not true. Okay? Because if x1 is negative, then 5x1 is in fact bigger than 6x1. Yes?
I'm kind of confused about your way of the proof. At the very beginning, I think
want to use proof by contradiction. You want to find a set which is over this number, and it cannot be achieved by this constraint. But now from this equation, I think you are trying to use some straightforward.
No. So what I'm trying to do is get what are called upper bounds on the profit. Okay. Whenever you find a solution, whenever you find a feasible solution, you get the associated objective value, right? That is a lower bound on the best possible profit, right? So now I already know one way to achieve $36,000 over $7. Okay. Therefore, the best possible profit for this particular problem is at least this quantity, right? Maybe there's a better solution, I don't know, but I know that it's at least this quantity. Now, if I have an optimal solution, then presumably there's also a proof that the best possible solution is at most that quantity. Okay? Now, this argument said that the maximum profit is at most 9,400. This easier argument said that it's actually at most 6,000. And the question is whether there's a way to actually prove that the best possible profit is at most this quantity. If we do this, then we know that here's a proof that one cannot do better than this quantity, and here's a solution that achieves that quantity. Therefore, this is the best possible. Okay? Is that clear? And is everyone comfortable with that kind of an argument? So if one can do this, then one gets excuse me. Excuse me. Then one gets a proof of the optimality of a particular solution. And if I tell you that there is a way to derive this in general for any mathematical programming problem, then you have a nice theory, right? Then you say that not only can I compute best possible solutions, I can also convince somebody that that's in fact the best possible and that one cannot do any better. Okay? Now, in order to do this, I want this verification procedure to be somehow far simpler than the method of actually computing the solution. So I'm not going to say much more about this now, but we'll pick up this theme a few lectures from now. Okay? But just to complete this line of reasoning, let me actually give you, for this particular example, let me give you a way to derive this. Okay? Yes?
You got the field that number 36,000. Where do you get that number?
Where do I get 36,000 over 7? It's just 5 times 4,500 over 7 plus 4.5 times 3,000 over 7. Okay. So Z is just the objective value evaluated at the current solution. How do I get this? No. So this is, I said, if we can get something like this, if we can somehow show that this quantity is at most something, which is at most something, etc., which is at most 36,000 over 7, then we know that the solution that's written there is the best possible profit. So this is something that we would like to get. We don't yet know how to get it. We don't exactly deduce backward. I just wrote down what I would, my desire to find such an inequality. I don't know how to do it, but if I can do it, then I would have a proof that the solution I have is the best possible. Now, so I've tried doing this a few times in the past, and this is either too trivial to people or it's too difficult, and not too trivial. Okay, so so let me actually now show you what exactly I mean by this. Okay, then it may become clearer. So what I want to do, so I'm going to get rid of this. So let me take 1 times 20 and 2 times 550. Okay, so just bear with me a moment. So when I do this, I get 200x1 plus 400x2 is at most okay, and when I do this, I get 6 times 550 is 3,000. Okay. So all I've done is just multiply. All I've done is just multiply each of these constraints by some numbers, okay? Which I'm not telling you how I got those, but let's say that we have those. Then I just add these two inequalities that I get. Notice that unlike what was first suggested, I'm multiplying only by positive numbers. Therefore, the inequality direction is preserved, and I can add. When I do, I get, 3,500 x1 plus 3,150 x2 is at most. This, it's hard to tell. This has one less. This is actually here. Okay, it's about 10 times smaller, and you get 3,600,000. Okay. And if you divide everything by 7, or 700, I guess. So divide everything by 700. So this divided by 700 is at most this divided by 700. Okay. And you get 5x1 plus 4.5x2 is yes.
First number in the first line.
This one?
Yeah.
200, yes. So all I'm doing is I took this inequality, multiplied it by 20. I took this inequality, multiplied it by 550, and I added. And I get something that says that this quantity is at most 36,000 over 7. And of course, magically, this quantity exactly matches the objective function that I have. And so this proves that if you find any x1, x2 satisfying these two inequalities, then the largest possible value of the objective function is this. Okay. So, if I somehow find this solution, and if I somehow find these two numbers, then not only do I have an optimal solution, I also have a simple proof that that solution is optimal. So I can explain this to anybody who understands linear inequalities, and this person may not even be intelligent enough to actually compute that solution. You can convince somebody that one cannot do better than this. Is everyone comfortable with this argument? Okay, you have a question.
Yeah, I'm just curious about the number 20 and the 5.
Right?
We do like 2 and 55.
You could do just 2 and 55, yes.
So then this pair number is kind of like any kind of multiples of 2 and 55 or something like that.
So you could use any, I mean, if you notice the actual numbers that I use to get this proof are 20 over 700 and 550 over 700. Okay? But you can, certainly, I mean, those numbers are carefully chosen, and I'm going to tell you how. Okay? But at least it should be striking to you that one could do something like this. Now, I also want to go back to the first or the second suggestion that we had. The second suggestion that we had did exactly this, except that it used 0 for this, 0 for this, and 1 for this. Okay? In other words, this proof, you can look at this proof as though it used multipliers of 0 for the first constraint, 0 for the second constraint, and 1 for the third constraint. Okay. The proof that I have shown you here uses 0 for the first constraint, 20 for this constraint, and 550 for this constraint. Okay. So it's I mean, qualitatively, it's the same thing. You're just using different sets of numbers because they just happen to work. Okay. Yes. Okay, so the short answer, so the question is whether 20 and 550 were derived from some kind of a Lagrangian theory, and for those of you who have not heard it, you don't have to worry about it. The short answer is it does come from some kind of a dual problem, which we'll get to in a little bit. So now one of the striking things about linear programming problems, and we'll have to say a little more about that in later in this lecture, is that for any linear programming problem, it's always possible to find numbers that play the roles of 20 and 550 here. So in other words, if you're asked to solve a linear programming problem, it's actually not too difficult to get these numbers in addition to the solution itself. And most methods that find solutions to linear programs also spit out these numbers that you can use to prove to somebody that this is best possible. Okay. Now, so I want you to also recognize that this is quite remarkable, right? So you have a feasible region consisting of infinitely many solutions, and yet without looking at all solutions, but just by giving you a pair of numbers, I can convince you that a particular solution is the best possible. Okay? Of course, it better be the case that such numbers exist only for the true optimal solution, right? Because otherwise, if I have a solution with value 5,000, and I have a pair of numbers that get me a proof that the best possible value is 5,000, then this solution cannot be right. Okay? So this is a very delicate set of numbers, right? That they exist provided you have the right solution. Now, as was pointed out, of course, the natural question is how does one get these numbers in the first place? Okay? What do they mean? And we will get into those issues later in the course. But for now, at least this should convince you that by doing this, I have a way of deriving this inequality that proves the optimality of the solution that I computed somehow. Okay, any questions? Okay, very good. So, those of you who have some background in computer science, I don't know if there's anyone here, but it's just worth mentioning that mathematicians and computer scientists have worried about proofs. Okay, so what does it mean? What does a proof really mean? Okay, so you run some computation and you have an answer. Okay? Now, how does one believe that that answer is right? Now, one solution to all of this is, of course, have this person, the skeptic, understand the problem, the theory, the actual method that's used to find the answer, etc. Educate him on all of those, and then he accepts that this is the right answer. Okay? But also, there are easier ways to convince somebody that you have the right answer. So there are, people have always paid attention to the difficulty of actually finding a solution to a certain problem and the difficulty of verifying whether a given solution is in fact right. Okay? And these two questions are sometimes very closely related. Sometimes proving is just as difficult as verifying. Sometimes verifying is substantially easier than proving. And there are people who study formally all of these aspects of computation. Okay, so let's actually do something else with this problem that will motivate our method of solution. Okay? Just so we still have the same linear program, and let's say we don't know what its optimal solution is. Okay? So now we do know what its optimal solution is, but let's forget that for a moment. So I give you a linear program like this, and we have no idea how to begin. Okay? So, well, short of this graphical method, where you can just graph the region and then visually identify the best possible point. Okay? Now, let me give you another linear program, and let's actually see how difficult that linear program is to solve. Okay? And all these numbers will give away the main point, but I think it's still worth making. So I want to maximize just bear with me for a moment when I write all of this down. So now obviously these two linear programs are related, but let's actually just focus on this. I want to maximize a certain function. Okay. I want to maximize a certain function, and I have these equations. Okay? So this just says x1 minus 1 over 14 s2 plus 2 over 7 s3 equals this quantity, and so on. I have all variables non-negative. So in this problem, I have 5 variables, x1, x2, s1, s2, and s3. The question is, can we solve this linear program to optimality? Now, what's the optimal solution to this linear program? Okay. Is the question clear? So I just give you a linear program involving 5 variables, 3 equations, and I want you to identify its optimal solution. Yes?
S2, S3 cannot be negative. It's like say equal to 0, and then you get the maximum number, which is 36,000 over 7.
Okay, so very good. So the observation is, if you look at the objective function, the only variables are S2 and S3. Okay? Now, the values of the other variables does not affect the objective value. Okay? They may indirectly affect the objective value because they determine what the constraints on S2 and S3 are, etc. But directly, they don't affect the objective value. So I just have to worry about figuring out appropriate values of S2 and S3. Okay. Is everyone with me so far? Now, given that S2 and S3 have to be non-negative, given that they appear with a negative coefficient, any positive value that I set for S2 or S3 is going to take money away from me. Okay? So the smart thing to do would be to set S2 and S3 to 0. Okay? So putting it differently, the best achievable profit in this problem is going to be 36,000 over 7. Okay? Because any feasible solution is going to have non-negative values for these two, and if I use any positive value here or here, my profit is going to go down. So the best thing that I can do is check whether I can set these two to 0. If by setting S2 and S3 to 0, I get a feasible solution to the problem, that has to be an optimal solution. Okay? We don't know that setting S2 and S3 to 0 will give us a feasible solution. But if it does, then that's an optimal solution. Okay? So let's actually try that. So if I set S2 to be 0 and S3 to be 0, then I get from here x1 equals 4,500 over 7. Okay. From here, I get S1 equals 1,100 over 7. And from here, I have x2 equals 3,000 over 7. Okay? That, of course, gives me a feasible solution, right? Because all of these variables, for feasibility, they just have to be non-negative. And they are non-negative. Okay? And therefore, if I give you this linear program, you can just solve it by inspection, right? You just look at the objective function, note that you have all negative coefficients for the variables. Therefore, try setting all of those to 0 and check if you have a feasible solution. And here we do, and therefore we just stop. Right? So this is a particularly simple linear program that we can solve just by looking at it. Okay. Now, of course, this linear program is actually the same as this linear program in disguise. Now, you should not be able to see that right away. If you do, you wouldn't have to take at least the first third of the course. Okay? But notice that, so I can convert this linear program into one involving 5 variables, right? We did that last time. So let's actually just do that again. So I would say x1 plus s1 is 800. Plus S2 is 15,000, and plus S3 is 6,000. Okay. So this also has 3 equations, 5 variables, all of them non-negative. Okay. The reason why this is not easy to solve is because we have positive coefficients in the objective function. And so now we are left with the task of determining what values to set for x1 and x2, which is really just the problem itself. It's just restating the problem. Whereas if I go to this representation of the same linear program, then that difficulty just goes away, right? Because the variables in my objective function are all negative coefficients. They all have negative coefficients. And I have non-negativity constraints, so there's a natural bound on how low they can be, and I set them to that lowest possible value. Okay. There was a question somebody had. Yes?
What we need to do is change the form to this form and eliminate the exponent to the form of x1 and x2 and 3.
Yes, very good. Okay, so the suggestion was to go from here to here. You just had to do some elementary operations involving variable elimination, or not elimination, just rewriting the system in a certain way. And the answer is that that's exactly right. But let me slow down, explain a few other things before we get to that. Okay? So if I give you this linear program, we don't know how to solve, but if I give you this linear program, we know how to solve just by inspection. Okay? Now, in this particular case, of course, I've done all the computation ahead of time, and I'm just giving you the final answer, just like I gave you the 20 and the 550 in the previous discussion. But what will be good is for us to understand just what it is about this representation that helps us solve the problem easily. Okay? And then what we could do is work towards such a representation so that we can easily solve the problem. Okay? Now, in going from one representation to the next representation, you want to preserve all solutions. Okay? So you want to, any solution to this problem should be a solution to this problem. And any solution here should be a solution here. Okay? So we want that property. So how do we verify that this linear program and this linear program are exactly the same thing? Well, you could see, for instance, what the main variables are, right? So So you want to rewrite your system of equations in such a way that instead of that you use S2, so you eliminate x1 and x2 from the objective function. Okay. So the way you go from a system like this to a system like this is by what are called elementary row operations, which just involve multiplying some row by a constant or adding a constant times a certain row to another row and so on. So you would have done these, if you had a class in linear algebra, you would have seen how to do these things. It also goes by the name of row reduction or Gaussian elimination, and we will actually do this formally next week, possibly next Thursday or the Tuesday after that. Now, for those of you who've seen linear programming before, one could think of the simplex method, which is a method to solve linear programs, as a way to go from a representation of this sort to a representation of this sort. Okay. Of course, you don't go from here to here in a single step. You actually do this as a sequence of steps. In every step, you do an elementary row operation that preserves all solutions. You keep going until you get a representation of this form. Okay. So the reason I bring it up now is that when we do the simplex method, it's useful for you to keep this picture in mind, that what we are trying to do, one way to think about what we are trying to do is to get a representation of the same linear program in such a way that you can be convinced of the optimality of a solution just by inspection. Okay. Okay, so something else I wanted to do. Do people remember the multipliers that we used in the previous proof? 20 and 550, right? It was 20. If you remember, it was actually 20 divided by 700. Okay? And the other multiplier was 550 divided by 700. Okay? Do people see these numbers in that representation somewhere? Okay. So this, if you simplify, is just 1 over 35. And this, if you simplify, is 275 over 350. You see them here. So again, this is not a proof that this is how you get the multipliers, but it should convince you that if you get the right representation of the linear program such that it's visually a no-brainer for you to solve, then somehow these multipliers are involved in some respect. Okay? This is not a coincidence. It's always true. So, as I said, all of these observations are not meant to intimidate you or to tell you that all of this is difficult to understand. It's actually just to show you all the things that you should be looking for when we discuss methods to solve linear programs. Okay, so I want you to observe that all of these things are somehow embodied in the way we solve a linear programming problem. Okay? So over the next few lectures, we are going to discuss systematic methods of solving problems of this sort. And that method will involve going from a representation like this progressively to a representation like this, where we'll end. And once we end there, that the last step contains a lot of information that's relevant for the actual problem. For one thing, it gives you a simple way to compute an optimal solution, and another, the coefficients of the objective function in that representation will give us some information about the right multipliers to use to get this other kind of proof. Okay? So we are going to systematically explore this class of problems starting from the next lecture, and also make sense of all of these observations that seem like just unrelated observations. Okay, okay, so any questions about any of this? Yes?
Is there ever a possibility that there will always be something like positive there that you can?
Okay, so the question, so the comment is it possible, is there a situation where no matter what you do, some coefficient here is always positive? Okay. So that you cannot use an observation of this sort. Okay. So if you find that some variable occurs with a positive coefficient, then you will try to do something with it. Okay? You will try to increase its value. So if you notice, all the variables that appear here we assume that they have 0 value. Okay? Now I'm saying something that I shouldn't really say because it comes as part of a particular method to solve problems. So those of you who know the simplex method, what I'm going to say will make sense, and for those of you who have not seen it, don't worry about it. Okay? So the simplex method will start by setting all of these variables to 0, and then checking whether the remaining solution is feasible. Now, if there's something with a positive coefficient, that variable is set to 0 in the current representation, so it will try to increase the value of that variable. And the next representation you will get by figuring out what the extent of that increase is. So in other words, if you keep on doing this and you always find that something occurs with a positive coefficient here, that cannot happen for too long. Okay? So you will, if you end, you will end with something like this. Now, it may be that the particular problem you have, you can achieve unbounded profit, okay, in which case you will have discovered that ahead of time. It may be that the particular problem you have has no feasible solution at all, in which case you will discover it along the way. Okay? So the short answer to your question is that can't happen because one of these other possibilities would have arisen before you end. Okay? Any other questions? Okay, so the problem that we've dealt with so far is what's called a linear programming problem. Okay? Now, why is it called that? Because the objective function is a linear function of the variables, right? If I double the value of any variable, I get exactly twice the profit. Similarly, if I double the value of these variables, I consume twice as much resources, and so on. So there's this proportionality condition that is true. Okay? It's also a continuous programming problem in the sense that the variables are allowed to assume any real number as its value. There are many realistic situations where neither one of these assumptions is true. For instance, even in this particular example, where x1 and x2 represented chips of certain types, it doesn't make sense for x1 to be, 623.7, right? Because you can't make those many chips. It's either 623 or 624. It could be that you make everything only in units of 100, so it has to be either 600 or 700. So there are many natural problems in which you have some kind of a discrete constraint embodied in the definition. Okay? So those kinds of problems are called integer programming problems, or discrete optimization problems, where the set of feasible points is a discrete set. Okay? We are going to look at problems of that sort also, but not as extensively. Now, one way to solve a discrete problem is to assume that the variables are not actually discrete but are continuous, solve the associated linear continuous problem, and then, if you get fractional values, then do something with it, massage them, round down to the nearest integer or something. Okay? Now, such an approach is a heuristic approach to solve discrete optimization problems. It may not always give you the best answer. Now, it turns out that actually linear programming problems, the continuous kind, can be solved very efficiently. Okay? Unfortunately, the linear programming problems of the discrete type, where you have discrete restrictions, they are much more difficult to solve. In fact, for problems of that sort, you may not have these kinds of multipliers, right? You may not. So what does that mean? You may, in fact, be at an optimal solution, but your computational procedure may not even be able to recognize that it's the best possible. Okay? So let's think about this for a second. Now, when you solve a linear programming problem, let's say that you have this feasible region, and you are at some point, and you keep moving around to better and better points. Okay? Now, sometimes, if you imagine that you have a problem like this. Let's say this is the objective function value, and you're trying to maximize. If you're somewhere here, then of course you recognize that if you move this way, you are increasing your objective value. Okay? So you keep moving, and maybe you're here, but you don't. Now you're at a point where, when you look around, every other point has a lower value. Okay? But if I show you the entire picture, you know that this is the optimal solution in this particular problem. Okay? But if you employ a search procedure of any sort that only looks at local information, you may in fact stop there, thinking that this is the best possible, because no matter what you do, you're going to decrease profit, at least in the immediate future. Now, one of the difficulties with problems in which such multipliers don't exist is the following. If you solve a linear programming problem, you know that multipliers of that sort exist. So wherever you are, you can somehow check whether you are at the best possible solution. Okay? And if this check fails, then you know that, okay, no matter what is said, you're not at the best possible solution, you can move along. Now, for discrete optimization problems, the difficulty is that you may in fact be here, okay? But there's no way for your procedure to distinguish being here from being at any other point. I mean, there's nothing like this duality theory that helps you recognize that you're already at an optimal solution. Okay? So we'll come back to this point when we discuss integer programming problems, or discrete optimization problems. So one of the nice things about linear programming and a slightly more general class called convex programming problems is that you never have local optimal solutions like this. Okay? Anything that's locally optimal is also globally optimal. So such a situation cannot arise in a linear programming problem. If you plot the objective value as a function of the feasible region, you cannot have things like this happening. Okay? Now, the other generalization is that you don't have this proportionality thing working for you. So we already talked about it in the context of the machine scheduling problem, where it may be that you get 100 chips after 6 hours of work, but you get nothing after 5 hours and 45 minutes. Okay? So there are these nonlinear and discrete events that happen only at certain points. And all of those can be captured in more general formulations where you don't assume these kinds of proportionality constraints. Another common feature is quantity discounts or fixed cost for setting up a machine for production. So if you want to capture features like that, you have to resort to what are called nonlinear objectives or nonlinear constraints. And in that case, all of this theory breaks down too. Okay? So the way the course will be run is that the first third of the course, we are going to focus mainly on linear programming problems. Then, for a little while, we'll focus on linear programming problems with a lot of structure. So these are what are called network flow problems, transportation problems, assignment problems. So these are special classes of linear programs for which there's a visual structure so we can actually see what's happening. Typically, these are formulated as problems on graphs. And when we discuss this, we'll touch upon various realistic problems involving, assigning objects to people, matching people, transporting supplies to satisfy demands in a network, and things of this sort. Okay? So those are typically, they are integer programming problems, but they have a nice property that makes us solve them as though they were linear programming problems. Okay? So you can ignore the fact that all of the quantities are supposed to be integers. You solve the linear program, magically you will always get integer solutions. So they are very, very special classes of linear programs. So we'll study those soon after that. And then we'll study integer programming and nonlinear programming very briefly. And there are classes that deal with these models in detail that if you're interested you can take. And finally we'll study what's called dynamic programming that I'll tell you about in a little bit, which also involves optimizing over time, but it's applicable in certain situations, and we'll not only learn how to apply the method, we'll also somehow, by looking at a variety of examples, understand what kinds of problems can be solved as dynamic programs. Okay? So this is roughly the plan for the entire course. If you go to the home page, which is a link off of my home page, you will see a syllabus that just lists all of these topics. Okay? And I briefly showed it to you last time. So I think I have about 5 minutes when I want to show you a couple of examples of just problems. We won't solve anything. Has anyone bought the textbook from the Columbia store? Or did anyone look for it at the Columbia store? Do they have it? Okay. So that's one place to buy. We are on tape, so I won't say anything more. Okay, so I want to leave you with a couple of problems again. Okay. Okay, so here are some other problems to think about. We will not get anywhere near to solving them now, but I think they are interesting puzzles that are worth thinking about just for fun, I think. Okay? And I'll probably put these on the web. So everyone knows tic-tac-toe, right? So two-dimensional tic-tac-toe. We have something like this. It's called noughts and crosses. It goes by lots of names. And so two players take turns, filling a particular cell. And if you get 3 in a line, you win. Okay? So you could do this, and then somebody else does this. Then you do this, and this person does this, and you do this. This person does this, you do this, does this, you do this. So that's one sequence of moves that end up in a draw. Okay. Is there anyone who doesn't know this game? Okay. Now imagine a three-dimensional tic-tac-toe. Okay. So you have a cube, and now people, so all of this just takes place in 3 dimensions. Okay. Now you have a win. So in other words, you have 3 layers of this. Okay. And you have a win if you have a line within a layer or a line across layers. Okay. The question is, what happens in 3-dimensional tic-tac-toe? Okay. So can the player who plays first always win, or can the player who plays second always win, or does it always have to end in a draw, assuming that people play rationally? Of course, as anybody who's played this knows, this will always end in a draw. Okay? I mean, if you lose this, then you're doing something really wrong. But how would you think about the 3-dimensional tic-tac-toe problem? Okay? So if you think about it as a math programming problem, then really, you want to determine let's actually think about this as a math programming problem. Okay? So player 1 gets to put 5 x's, and player 2 gets to put 4 noughts. Okay? So for every, so you want to have a variable that indicates which cell you're occupying at which point in time. Okay? So think about how you would formulate this as a mathematical programming problem, just like we formulated the flexible machine scheduling problem as a math program. How do you formulate this? Once you get that, then one can actually think about formulating a 3-dimensional version as a math program, and you could check whether that can end in a draw or not. So again, the answer is not important, but the idea of actually writing down a formulation using variables and constraints is a good exercise, okay, even in this case, and I urge you to think about it. Of course, you cannot use, the variables only represent whether or not you use a particular cell at a particular stage, okay? So it would be what are called Boolean variables, so binary variables, 0, 1, okay? So you would have to work with that. So this is a natural integer programming problem, okay? Here's another problem that again doesn't seem very relevant, but let me just mention it. So you have a car, and the car consumes, it gives you a mile per gallon, okay? Not a particularly good car, but that's all you have. And you have a fuel capacity of 500 units, okay? So you have this car, capacity is 500, and its miles per gallon is just 1. Okay? But of course, you want to travel 1,000 miles. Okay? So this is where you want to get to. So this is 500. Okay? There are no gas stations along the way, but there's a gas station with infinite supply here. Okay? You don't have any approved container to carry gasoline. So really, the only gasoline you can carry is Well, you don't have any approved containers. The only gasoline you can carry is in your fuel tank. So in other words, you can carry only 500 units at a time. But you can make fuel depots along the way. So in other words, there are containers at every point in this line that you can fill and then reuse. Okay? So if I fill up and I drive all the way through, I get to this point and I can't do anything. Okay? If I fill up, drive, a third of the way through. Okay, so this is 500 over 3. Okay, store 500 over 3 here and drive back. Okay. And I can again come, and when I'm here, I will have exhausted 500 over 3 units, and I can use this quantity to fill up my tank and proceed 500 units from here. Okay. Does everyone understand the problem? So the question is, what is the most fuel efficient way for you to actually get to the destination? Okay. Now, of course, this is, it's phrased in terms of cars, and but this is, it's not a real problem. It's just a puzzle. But again, it has the following nature, that you have to make decisions, and you have to make decisions over time, and your decisions are all interrelated. So the first depot you establish here may mean that if you do this, then the second depot has to be somewhere else, and so on. So given that you have to get to this point, what's the best way for you to travel to minimize the total amount of fuel used? Okay. So there are, tons of other puzzles that I have that I can, I'll probably put a few. You can think about, not only solving them. So this, I think, is worth trying to solve. Okay. So how would you solve this problem? And it's perfectly within the reach of each of you. Just don't Google. Okay. So try to solve it yourself. It is a lot of fun. Okay. But don't try to formulate it as anything yet. Okay, so for next lecture, we'll do some more serious things. So we'll start with the simplex method. Before that, we'll actually do the graphical method that was suggested. So I urge you to read chapter 1 and chapter 2 of your textbook. That almost covers what we discussed in these 2 lectures. Okay. So go through those, and then we'll pick up things from chapter 3 from the next lecture. There is going to be a homework, and I'll send you an email once it's posted. It'll be a simple, couple of problems, very straightforward.
I think that's what you know.